Good morning from New York City. Another nice day here, a nice autumn or fall day, call it what you want. Going to continue with Newton's laws and applications thereof. Now, the other way to look at this is through Lagrange's equations. We're going to deal with friction. One of the conditions that I posed on Lagrange's equations when I did it the last time is that Lagrange's equations, as I stated them, were valid only in the absence of dissipative forces. Well, what's a dissipative force? Friction. But I will show you how to handle Lagrange's equation adjusted to include dissipative forces in the special cases that we normally study at this level. And that is just simply constant friction, or it could be also constant air resistance. Because even using Newton's laws, you guys can't really do much more than ordinary constant friction or constant air resistance. So those cases we can deal with quite easily with Lagrange's equations also. Very neat, I'll show you. Right. Now, people often say that these are situations where energy is not conserved. That's a totally false statement. Energy is also conserved in the presence of friction, right? Where does it go? Well, you could work out exactly where it goes if, for example, the friction surface, right, was totally insulated. Let's say it's styrofoam, but that the object that you were moving along and that was experienced the friction, let's say had a certain mass. Certain mass and a certain specific heat. Then you could calculate the number of joules of heat energy that the block would take up, right? Would take in. In the system consisting of the surface, the block, let's say the air if it's there, that's the system, energy is still conserved, does not disappear. It just goes from one form into another. Now, I'm going to leave Lagrange's equations aside because I'm going to do more problems. We'll end up doing problems that look like this. A slope, just to make things more awkward, with an alpha, a block sliding. We could put in a pulley as well. And a pulley could have mass and a moment of inertia. We can deal with all those situations. And there could be friction too. We'll deal with all of those things. But first of all, I will remind you what we mean by Newton's laws. The first law is the law of inertia. It is a law of physics, a law of nature. And it is one of the only laws of nature, one of the few anyway, that we cannot write down an equation for. The reason we cannot write down an equation for it is this. It's just stated to be a law. We don't know why. Physics began, if you like to call it physics, I prefer to call it natural philosophy like Newton called it. Physics began, or natural philosophy, began with the law of inertia. Before that it was kinematics. Okay, so Galileo discussed free fall. So well, yeah, let's say it began with free fall. But on the way to developing what we call physics, we had a formulation of the law of inertia. It's the first of Newton's laws, or it's Galileo's law of inertia. I don't care who gets the credit for it. One way or another, it's a law of nature. It cannot be ignored, it's there. But we have no equation for it because we don't understand it, right? But I will tell you something. It's intimately related to gravitation and it's intimately related to circular motion, right? Centrifugal force. People in textbooks hate that word. I love them. All right, so those things, centrifugal force, inertia, and gravitation are connected, but we have no little equation to show the connectedness of them. So the laws of Newton are, first of all, the law of inertia really defines the beginning of recognition of mass, inertial mass. That means if you have a lead block and you try to kick it, you try to accelerate it, right? You'll hurt your foot, okay? Now that same inertial mass will persist in space. You try to kick the same block in outer space, you'll have the same pain in your foot. Now that's the first law, the law of inertia. An object continues at rest or in straight line motion, uniform, unless acted upon by an outside force. Second law. Force equals mass times acceleration. If you want to accelerate that block, change its state of inertia, that is, you have to apply a force to it. And what's a force? A force is a push or a pull which changes or tends to change the state of rest or uniform motion of a body, of a mass that is, really. Okay. Now you can go and look at my lectures on gravitation and you can see the difference between gravitational and inertial mass. And why they're the same, we don't know, okay? Go into my lectures on gravitation when you finish these ones. Okay, so force equals mass times acceleration. The third law, for every action there is an equal and opposite reaction. To my mind, there's nothing to do with reactive force, nothing to do with the normal force. That is a statement of the conservation of momentum, all right? For that we have to go back to the Royal Society with Christopher Wren and a long story. Okay, so what we're doing is we're looking at the applications of this, and a force can be represented by a vector. A force is not a vector itself. The vector is an object that keeps track of components. Let's look at the way force can be represented by a vector. Well, you know this, but we're just going over it for the record. So here's a force. It's pulling a ship. It will have a component in this direction, which is the projection, parallel projection of this vector onto this axis. It will have a component in this direction, which is also the parallel projection of this arrow into the vertical direction. So we've effectively constructed a triangle here, and there's the opposite, and here's the opposite. The length of this one here. H sine theta is going to be the opposite, so we can say that Fy, the y component, and Fx is the x component, is going to be, call this F. The magnitude of this vector is given by Pythagoras' theorem, the square root of Fx squared plus Fy squared. So we have Fx and Fy, F sine theta and F cos theta, such that the vector itself can be written in its components. And the length of that is given by Pythagoras' theorem. Okay, so let's get rid of that on the board. Now we have some special forces. Weight, we've already said, is mass times acceleration, but the acceleration due to gravity. Okay? And on a flat Earth, it just pulls directly downwards. We approximate flat Earth because locally this room appears to be flat. Now the friction force is going to be mu n, whatever that is. We'll say what the n is now. First, the normal force. Here we have a table. We put a mass on it. Now the mass experiences its weight in the vertical direction. But wait a minute, the mass is not moving anywhere. It's not accelerating downwards because there is a resistive force pushing upwards for it of magnitude n. The normal force. N is the normal or normal to the surface. It does not have to be vertical. We'll show you that in a minute. So minus mg is one force acting on this mass, and I'll get rid of the vector notation. The mass has no acceleration. So the sum of these forces is 0, so we can say therefore then that the n has a magnitude of mg. In this case here, the normal force is vertical. All right, let's look at tension. We've done that one, we've done that one, and now tension. We'll hang a mass by a string. What is the tension? Well, if I decided to hold that string with my fingers, I would feel the tension in the string. Tension is the pulling force in a string. It's what keeps it taut. So, what is it? Well, we'll call it T. T is working upwards, kind of like the normal force, and mg is pulling down. But the mass is static. It has no acceleration. If it has no acceleration, I can write down that the sum of the forces on it add up to 0. So that in this case here, the tension in the string is just mg, just like the normal was there a minute ago. Instead of the normal, we have got a tension. This is a convention that helps us to solve these. When you go and look at the Atwood's machine, I could have solved it using tension, but I hadn't discussed tension, so I didn't use the tension. We'll now deal with friction. There's our table. There's our mass. Now we'll pull the mass to the right. We'll feel that it takes a certain force to keep this mass moving at constant velocity, constant speed. That force is due to the rubbing between these surfaces. That is the force of friction. Now, how can we write down something for the force of friction? Well, if I double the mass, I will notice that that force will double. If I make it 3 times the mass, that force will triple. And if I change the nature of the surface here, I could affect the amount of pull I need to keep it going at constant velocity. Now, there's 2 different pulls. The one that we have to use just to get the mass to move, and the one to keep it at constant velocity. Keeping it at constant velocity requires a lesser pull than just to get it to move. So we'll call this static friction versus dynamic friction. We're not going to consider static friction at all. It's always constant velocity friction. Now, this could have equally well have been a push. I just put the pull there. So let's see, what's the magnitude of the pull? Well, it's something to do with the normal force. The force that's needed to maintain that in vertical equilibrium is the normal force. In fact, we'll put in a number to, account for what we don't know. In other words, the nature of the 2 surfaces. This number, which I'm going to call mu, is going to be called the coefficient of friction. In our case, the coefficient of dynamic friction. This mu can vary between 0 and 1. It can never be 2. The most force I can operate to pull this object can be equal to the weight of the object itself. So, what was the normal force? A minute ago we calculated it to be mg. So the force of friction is in the negative direction, but I'll just say for now, mu mg is its magnitude. Okay? Now we're going to complicate things for students. That's everything covered. But for students, we put things on angles, and we add pulleys and all sorts of things to confuse you. So, to deal with things on a slope, we're going to end up with a diagram in our minds that we're going to remember. we're going to remember the components of weight in those directions. Pardon me, I just knocked down my little table. In those directions, they're going to be the components of the force. Let's see why. There's our alpha. I call it alpha. Some people like to call it theta. And here's our mass. It's going to get pulled down by the force of gravity, whose component is directly down because I'm going to choose an axis. I'm going to choose the axis which is going to be normal to our surface. So therefore then, this is x, and so is this. It's the negative x direction. Now we ask the question, what is the component of force this way? Well, let's see what this angle is. If that's alpha, there's our component of force. Here's beta. Beta is 90 minus alpha. There's 90. So therefore, that's alpha, right? So we put our vector sideways so that we can see it more clearly. So that's F. This is F cosine alpha. F cos alpha. Right? That's F cosine alpha. This is F sine alpha. Let's see what the normal force is for this particular case. The normal force acts this way. So if we want to add up all the forces in the y direction, I have minus, and F is mg, minus the weight plus the normal force. The normal force is now following this angle. But there is no acceleration in the vertical direction. So I can write down n is mg cosine alpha. Now suppose that the object is actually moving. And friction is preventing it from moving anything more than but at constant velocity, right? Or an acceleration, actually. So I can say then that in this direction, we're going to have mg sine alpha pulling downwards. What are all the forces in the y direction? Minus F sine alpha minus mg sine alpha. Now the force of friction is opposing this. Plus mu n. Well, mu n, we found m is mg cos alpha. Now, the motion is not constrained in this direction. There could be an acceleration, right? We could be moving at constant speed, or there could be a net acceleration. So we have to say, some of these forces is ma. So let's see what they are. So I can find the acceleration. Now in the next roundup, I will show you guys how to find this equation of motion, in other words the acceleration, using Lagrange's equation. I can cancel through with the m's and write an expression, The m's cancel. For the acceleration, A is g times mu cos alpha minus sine alpha. So remember that for when I do Lagrange's equation next using friction, but friction being present in Lagrange's equation. Okay? Nobody ever teaches people that. So now let's do something else. I could have this situation. Let's clean the board actually. I'm going to put tension in there now instead. Cleaning the board. If I can find the eraser. Now I can't remember what I got. Was it sine alpha? Something like that, I think. All right. Okay, so let's add tension. We do the same problem, but this time it's been held fixed using a rope. Now in this case here, there is no friction. This time we're just asked to find the tension if this is m and this is alpha. Okay? All right. So in this direction, there is no motion. We don't have to consider that motion at all. We just have to consider this motion. So remember what we had here. We had minus mg sine alpha as being the force in that direction. Now the positive force, the tension force, operates to hold the block up. This is the x direction, this is the y direction, and there is no acceleration vertically, as it were, in the x direction, sorry, the y direction. So all we've done is we've adjusted t from being mg, which was the vertical case, to including a sine alpha in there. Yeah? So you can play around with these things any way you want. You can add friction. You could add a pulley. I could put a pulley here. And we could get the pulley mass, we could add a mass down here and so on and so forth. All those different complications just means extra handwork. There's very little extra thinking involved. Okay? Let's see. Okay, I'm going to stop this one right there until I do the next problem. And the next problem will be solving Lagrange's equation for something like this, but in the presence of friction. So you see how to include friction in Lagrange's equation.